Hi, my name is Mariano Zeron, and in this video I'm going to show you how to use the mocax library to approximate the derivatives of a given function. So let's dive into some code that I've got here. So far, what we've covered is how to build the mocax object in its most basic manner. So what it does is come up with a replica of a given function. Let's assume that the function you're interested in is a sine function which you got here. So one thing it does is create an object, which is the replica of the function. Then you can call the eval method so that you get back the values of that object which have replicated the function. Perfect. But the algorithms within the library allow you to obtain also replicas for the derivatives of the function without having access whatsoever to the derivative of the function. Now, how can we specify the initializer of the mocax object that you want to have the information or that you want to be able to replicate the derivatives of the function? That is controlled with a single parameter that we can check in the documentation. The parameter, let's go all the way to the top, the section of the documentation for the mocax class. We click on the initializer and we see the next to last parameter is called mocax derivative order. That comes with a default value of 0. 0 indicates that we're not interested at all in the derivatives, but only in the original function. But if you change that to another value, then the initializer will get all the information that it needs from the function and will come up internally with a replica not only of the original function, but also of the derivatives, up to the order that you've specified with the parameter max derivative order. So let's go back to the code. What do we have to do? So we specify the dimensionality of the function you want to approximate. Then you specify what the domain is. Specify what the size of the Chebyshev mesh is. And then finally, you specify derivative order that in this case I've put as a value of 2, meaning that I want to be able to have an object, a mocax object, that replicates the sine function, which is the function that I'm using as an example, but also of its first derivative and its second derivative. So I'm going to run this first part, which is the first stage of the building process. And I've got here a description of what I have so far. It says unfinished construction, meaning we can't use it so far. But the second part of the building process is the same as when we were not interested in derivatives. That is, we only evaluate the original function on the Chebyshev points, pass those values back to the object, and we are ready to go, which is this part of the code that you see down here. And once it's finished, I've printed the object, and we can see in the description, the last line says maximum derivative order 2. So this says that you'll then be able to call the eval method of the object, and you'll have the choice of getting back the values corresponding to the original function, the values corresponding to the first derivative, or the values corresponding to the second derivative. Now let's see how we do that with the eval method. So here, what I have is the building of the object in these very few lines because I've wrapped the previous code into these convenient functions. I can run them, and I've got the unfinished construction, you see here, followed by the finished object. Now what I do is, just as I did in the previous video, is call the method eval, passing it the point that I'm interested in, but also passing a parameter called derivative ID that indicates exactly which derivative I'm interested in. We go to the documentation. We can see that the eval method over here takes these two parameters, the second being derivative ID. And it's an identifier, basically. Now, it's important to be careful about the way that you obtain the identifier, because the natural or the intuitive way to specify derivatives is the following. Say that I'm interested in the first derivative of the function, which is one-dimensional, like in our case. I would like to write just bracket 1, or let's say the value 1. If I'm interested in the original function, it will be 0. If I'm interested in the second derivative, I would put 2. What happens if you've got a two-dimensional function? If I'm interested in the original function, given that I have two variables now, it's 0, 0. If I'm interested in the partial with respect to the first variable, I would specify 1, 0. And if I want the partial with respect to the second variable, it would be 0, 1. Also, if I wanted the cross derivative, that is the partial with respect to the first variable, followed by the partial with respect to the second variable, I can specify it as 1, 1. And this makes a lot of sense. But unfortunately, the object won't understand this description. So we first have to change this description to something that the object understands. So to do that, what we do is call the method getDerivativeID. And that getDerivativeID, what it does is change the derivative written like this over here and returns a derivative ID, which is what the eval method will understand. And that's the only thing that you need to do. So let's take this bit of code, wrap it, so that we can now visualize some of the results or some of the things that this object can now do. Now, let's take as an example the Black-Scholes function. And let's take the delta of that Black-Scholes function. We know that the delta is the derivative of that function. I'm not going to pass it at any point to the initializer of the object or to the object. So the object is completely agnostic of the delta function. I'm only going to use it to compare the values that we obtain from the mokex object when we ask it to evaluate the derivative and the derivative, which in this case is the delta function, in order to obtain the errors or see the errors that there is in the approximation. So first, let's build the object that we've built, as we can see here, between 50 and 150, because the strike is 100, so it makes sense. That range makes sense. N, which is the size of the Chebyshev mesh, is 15. I've asked the initializer to build me an object with a derivative order of 1, that is, it's able to replicate the original function and also the first derivative of the function. Now I evaluate the function, but I evaluate it with derivative 0, that is, I want the values of the original function. So I can evaluate it, no problem. Now I compare that with the original function, and we obtain what we expect. Basically, a call option and the error, which is around 10 to the minus 6 on the right-hand side. So all good. And what happens if we want to evaluate the mokex object, but asking it to give us back the values of the replica of the derivative? So first of all, I need to define derivative to be equal to 1. And then that is passed to this function, which essentially evaluates the object on all the points of the domain, but asking it to give us back the values of the derivative. And now what I'm going to do is compare the mokex values that we just obtained with the function derivative on those points. And this is the only time where we use the delta, finally, to compare the results. And what we obtain is this plot. So basically, we can identify the delta over here and the error on the right-hand side, which is also really, really small. It's 10 to the minus 6 or 10 to the minus 5, something like that, but it's really, really small. And as you can see from the code, this was done without having any access whatsoever to the delta function, only access to the original function. Is one of the really good properties that the whole theory of Chebyshev approximation has. So what I've showed you in this video is how to build mokex objects, but with the idea of not only replicating the original function, but also the derivatives of that function, and also how to evaluate these objects. In subsequent videos, I'm going to cover further functionality that the library offers. Thank you.